So I want to talk about 3D printing with polymers and just kind of consider what's going on at the polymer chain level, just from a 1,000-foot overview. So it can be handy to look at what polymer chains actually look like, the actual molecules, just to kind of get an intuitive understanding of what's going on. And so these figures generated by Komaki, they're AFM or atomic force microscopy images of basically molecules of polymers that are forced to be planar, like they're basically deposited on a single plane, so we can get this nice 2D image. So keep in mind, right, these are typically, they exist in 3 dimensions, and so this isn't a full representation of what's going on, but it's easier for us to parse. So you can see here there's actually 3 individual polymer chains that have this big interweaving kind of link in this spot here. So they're pretty much, for all intents and purposes, they're one big linked polymer that has this big kind of linkage thing in here. You can also see, right, polymers, sometimes you can have these short chains that align, so you have these small areas of order, right, and there's also, right, what do they call it? Small areas of order, but large areas of chaos, right? So you've got this small local order, but really you've got a bunch of things interlinked, and it's a little more chaotic the further you zoom out. Anyways, once again, the key thing to think about here is that this is being constrained into a 2-dimensional existence, essentially. But it's still kind of neat to see kind of almost this thumbprint pattern that arrives, or you can even see it even more thumbprint pattern in this image. Right, so there's a lot of linear chains here, right? There's not a lot of branching. And you can see kind of how they're all interlocked. And so what that means is there's some mechanical connection, right? The particles are actually literally just kind of linked around one another. Like you can see in this highly interpenetrated image, right? There's this guy's really captive in here, but this more segregated polymer chain, it's not as interlinked, right? It's basically just relying on like weak electrostatic forces like hydrogen bonding and van der Waals and things like that to hold it in place. But it would be much easier to isolate this polymer chain than it would to be this one. And you can even think, as you would imagine, right, if I were to apply a force here, probably my best place if I wanted to break this would be right here, because you can kind of see this like division across here, and that's where it's going to be easiest to break things. It's just kind of the way things are, is the more segregated the polymer chains, the easier it is to break them. So that the first thing I want to look into that's kind of related to that is self-adhesion, right? So when we 3D print, we're printing one layer on top of another on top of another, and so it's one bead of extruded plastic on top of another bead. And so when we extrude, it should be no surprise that we actually kind of force those polymer chains to align to some degree. And so they kind of have a net direction in the direction that we're printing. And when you are heating that up, obviously getting it to its glass transition temperature, you're also transferring some of that heat to the plastic right underneath of it and heating it up and putting it in its glass transition. And so what's happening, right, is if you think of this blue as like a cool layer, and this black is a layer that we're putting on top of it, what's happening is we have a lot of still isolated polymer chains, but they do still interlink a little bit. And there's 2 things that's happening, right? There's mechanical bonding, meaning that they're actually like linked around one another to a degree, right? These small little connections. There's also weak bonds like hydrogen bonding and all that stuff that causes them to align and basically electrostatically connect with one another. And so you could almost think of this interface, one layer to another layer, is similar to Velcro, right? We've got just this small connection. We've got so many of them that it is indeed connected. Well, the consequence of this is that usually the weakest component of the part is the layer interface, right? That's normally the weakest component. And so it's something you have to consider when you print your parts and when you design things, is that you're always going to be weakest along that right orientation of where your layers are. So for example, if you had a part that's printed like this and you were going to maybe like have a bridge or you're going to be stepping on it, that would not be the best because you've got these lines here that can just basically shear apart when you apply that force. Where here, you might get a little bit of deformation with enough force, but it's probably less likely to break than if it was in this print orientation. Yeah, so another thing to consider is bed adhesion, which is somewhat a similar thing, right? There's mechanical bonding and chemical adhesion that happens, right? So when you have when you're 3D printing on your bed, depending on what material, there's different things that they recommend that you do, but they usually the biggest thing is adsorption and mechanical connections that cause that to happen, right? So the first one, right, mechanical bonding is assuming that you've got a porous enough material that when your plastic is 3D printed, it basically goobers into there and then gets stuck in, right? It's connected in all these little teeny micro pores. Adsorption, it's a little bit different. Adsorption is basically those weak forces that I keep talking about that are like the van der Waals and the hydrogen bonding that cause the plastic to kind of align with whatever medium you're printing on top of. So that's what absorption is those weak forces. Chemoisorb, chemisorption. Sorry, it's a word I seldom say. Yeah, so that's actually you've got a chemical reaction that kind of literally causes things to actually chemically bond together, and this is a bond that you probably don't want with your bed because this is going to be the strongest one, and so it's not quite something you want. Um, Same with diffusion, right? Diffusion is your particles actually swap. So some of the particles of the bed get diffused into your print, and some of your print gets diffused into the bed, and that's usually kind of a uh, strong adhesive bond, but that's also something we don't really want. So usually, adsorption and mechanicals is what we have for bed adhesion with 3D printing. Yes, and obviously, good. Oh, criminy. Good bed adhesion is required for FDM, right? For 3D printing, you've got to have a good adhesion. And that's why I say when you 3D print, you should watch at least the first 2 to 3 layers before really walking away, because those are the most critical ones. If those aren't nice and uniform and stuck down solidly, you're probably not going to have a good print. And so for most consumer materials that you would buy, usually it just says what to do. So if you're like want to print with say PETG or PTG or PLA or ABS, just Google best bed adhesion for that material, and we've already figured it out, right? Scientists know what to do there. So you just follow them. But right, there are some cases when you're using novel materials, and you can't just Google things, right? I've ran into that in my research. Where I was using recycled low-density polyethylene, right? And so 3D printing with that, it was a bit of a challenge to have bed adhesion to what the actual bed and the printer I was using had. It didn't stick at all. So what do you do there, right? You can either become an expert in surface science. That's could be feasible. Maybe you're just good at that. Or maybe you could consult somebody that's good with that. The other thing you can do is just kind of experiment, right? Take things that have worked for other materials and try them out and see if they work for your material. Try some blue tape, try some packing tape. Maybe you put saran wrap over, maybe glue stick, maybe a hairspray, maybe some proprietary thing you found. And I found worst case scenario, right? Worst case scenario, if you need to get your print to start validating some results, uh, something that your material will always stick to is itself. And so my solution when I really wanted to get up rocking and rolling to start getting some preliminary results was I just put down a sheet of low density polyethylene to print on top of, and it worked. Obviously it like fuses together really well, um, but yeah, that's what I needed to get myself rocking and rolling. And yeah, so thermal expansion is something that will always haunt you for your bigger prints, right? When you're printing big things, these numbers mean more to you. Um, and so it's governed by this one equation. And basically, if you wanted to experimentally figure out what thermal expansion was, you would just have a piece of material and you would measure it, right? So you have a piece of material and you measure it at room temperature, and then you change its temperature, you have a delta T, and then you measure the change in length, right? You measure the change in length due to that delta T, and that gives you the thermal coefficient of expansion, thermal expansion coefficient rather, right? And so what that means is when you're 3D printing, you have uh, a hot material that's depositing that is now cooling. So it's right when it's hotter, it's a longer chain because things are kind of stretched out a little bit, and there's more energy in the material. And when it cools, it contracts a little bit and gets smaller. Um, so what that really means to you is it causes warping. You can see here, right? The biggest thing is you have a cold layer that's starting to cool down and a hot layer on top of it. And what that does is they kind of pull on one another because they're cooling at different rates and they're contracting a little differently. Um, yes, so the biggest thing is it will do is it will cause warping. And so there's three ways to solve this issue, right? You just try and find a material with the low thermal expansion coefficient, or you could make your own, right? So you could make composite materials, which is something we'll get to later, where you add material into your plastic that has a low thermal expansion, and then on a net basis, that whole material has a lower coefficient. So that's something that can be done and is being researched. Um, Strong bed adhesion, right, is something else you can have, right? So the stronger bed adhesion, basically the forces of your adhesion just have to be able to be stronger than the forces that are physically pulling things up. So if you've got good adhesion, you can prevent that. I've even seen some people actually mechanically clamp these down, or like tape down some parts of their print to prevent warping. And then the big thing is you can try and keep your print all the same temperature, right? So you can either keep it cool, so that's like you're cooling things as they print, so they shrink down to their temperature or to their actual dimension really quickly. Or if you keep it hot, it kind of keeps everything hot and uh, and expanded the same exact way, and then the whole part can cool down at the same time and prevent it from like warping or popping off. Um, yeah, so those are just a few consequences of the fact that polymers act the way they do that affect our printing that you should consider.